All right, good morning. I would like to recap what we did last time. So we looked at what's called gradient dynamics. In this gradient dynamics, we construct the equation of motion, the Lorentz equation for the fields, using the free energy. So that's our major player here. And once you have that free energy, and if you are in a system that shows relaxational type of dynamics, then there are basically two classes of dynamic systems. One is where the order parameter is a non-conserved quantity, and then you have local relaxation of the system to its thermodynamic equilibrium state. So you have an equation of motion, a Lorentz equation, where the driving force is local relaxation to equilibrium with a coefficient that's a Onsager coefficient, and the noise amplitude by the fluctuation dissipation theorem is related to the Onsager coefficient by 2 times the coefficient times temperature. In the lecture notes, I will actually also discuss the case where the kinetic coefficients are dependent on the state. Here I leave this out for simplicity, and then the relation is really just this, and there's no issue in terms of interpretation of the Lorentz equation. For the other model, where you consider a conserved order parameter density, the construction has to respect the conservation law. That means the density evolves in time according to a continuity equation with a current J. And then the current J is driven by gradients in the chemical potential, again with an Onsager coefficient and a noise term. And in a similar fashion, you can actually show that the amplitude of the noise term is also, again, given by 2LT. Okay, so that's relaxational dynamics. Today, I would like to study with you a hydrodynamics problem, basically the Navier-Stokes equations. And there you do have momentum conservation, you do have energy conservation. And that's a more general case where you see a lot of things that are more general than in model A or B. And you will also see the Onsager structure quite clearly in these systems. So I call this chapter here field theory or hydrodynamics for what's called simple fluids. Simple fluids is kind of a joke because these fluids are really, really complicated. When you look at the dynamics of those fluids, they're called simple here because they're just composed of one sort of particle, like water molecules or glycerin or something else. The approach I will do is, again, an approach where I assume local equilibrium. And that means I have thermodynamic quantities I can define. So I will define a temperature that's local. So it will be a function of position and time. In the same way, I'll consider another thermodynamic quantity, which is the pressure. And this pressure will then also be a function of space and of time. And the way you should think of this is always in terms of some small region in space on which you can use such kind of coarse-grained variables, and that's called in the field and in textbooks a fluid element. So it's just a large enough element in space where you can do the coarse graining and you can make the local equilibrium assumption. Okay, we want to specify the relaxation to equilibrium by linear non-equilibrium thermodynamics, and I will often just refer to this as Onsager's theory. And what this means is that you have some deviation from equilibrium, and those deviations from equilibrium are then relaxing towards equilibrium, and how they relax I will describe by phenomenological laws that are relating currents to gradients, and you will see what kind of currents I mean and what kind of gradients I mean. So in addition to that, I need some fields, and the fields that you want to consider have to be slow, because otherwise you would describe something on a more macroscopic scale. So you have to just reflect with the choice of your variables that you are doing a coarse-grained theory on large length scales and large time scales. So that means typically in a fluid, you would take the densities of quantities that are conserved because they are slow by their very definition. You need to transport things over long distances to change conserved densities. So densities of conserved variables is what you take. If you were to be at a more general system, not just a simple liquid, but let's say at a system close to a phase transition, you would also include the order parameter in this class, because the order parameter, as we learned, shows critical slowing down, so it's slow, and then you also need to account for the order parameter field as a slow variable. So what are those variables? It's the mass density, so the number of particles, the mass of the particles in a certain volume, rho of x and t. So it's not the number density, I mean here really the mass density of the system. I will also need, because it's conserved, the momentum density, and I call the momentum density here by the symbol g. So g of x and t is the density times the velocity. That's the momentum density. Right, so this is just the mass density times the velocity of the fluid element. That's what I mean by the momentum density. Well, there's another conservation law, which is conservation of energy. So you need to also consider the energy density, epsilon of x and t. And I mean, again, in the same way as I look at the mass density here, the energy density is per unit mass, not per unit volume. Okay. Per unit mass. What else? Angular momentum is also a conserved quantity. Okay. And I don't introduce a symbol because I won't really need it. So those are the variables. And now we need to construct the equation of motion, where I use all these things that you have here. And of course, what I shouldn't forget here is that all the symmetries that are in the system need to be accounted for. And if a fluid, this is rotational symmetry and translational symmetry. So now let's start with deriving the equations. And we start with a system that is frictionless. And I do it in stepwise fashion because I want to get you used to the concepts in fluid dynamics in a slow way. So that means we have no dissipation. This is what frictionless means, and all we do, we have to account for the forces that act on the system. Right, so let's start with the conservation laws. We certainly have mass conservation, and that means that there must be a continuity equation for the density. So the density must be written in the form that this is minus the divergence of a current of J and X and T, and the current in our case is just rho of X and T times V of X and T. Just the mass current that we have. Later on we will see other currents that play a role. Here this is just the mass current. Because we need it later on as well, let's consider a small element of space with a certain volume V and the boundary that I call delta V. And let's look at the integral form of that equation. Then what you get is the temporal change of the integral over the volume of the density. So meaning just the total mass that you have in your system. And this total mass can only change because of the term that you have here, which is the divergence of the current. And by Gauss's law, you can write this as a surface integral of the current itself. Okay. And the surface integral is here defined as such that I have a vector that's normal to the surface, and ds vector is the normal times the surface element ds, describing this little volume element. Okay. So n defines the outward normal. So then this is clear what this means. If you want to change the mass in this volume element, the only way you can change the mass is through the boundary by fluxes in or out. And that's what's described by that term. So the next thing I would like to discuss with you is just Newton's equations. And they are called, in the context of a frictionless fluid, the equation by Euler. So what do we have? If we look again at the same volume element, we can write the total term for the inertial term, which is now the density times the velocity derivative with respect to time. This will be given by all the forces acting on the system. Well, now you need to know what a pressure is, because that's what I need in order to write that down. The pressure is acting on the boundary of the system, only there. So all the forces that I have that act on the fluid are the negative pressure acting on that fluid element. So this has to be this boundary integral ds p of x and t. And again, I'm using Gauss's law, and I can rewrite this as a volume integral, here over the volume, here over the boundary, here the same thing, over the volume here over the boundary. This is then minus the gradient of the pressure. Okay, so that means now, because that's true for any volume element, we do have indeed Euler's equation in this form, which says dV dt times the mass density is driven by the forces coming from the gradients in the pressure. So what you have to note is that I carefully wrote here always this symbol, d dt, while I do have two variables here, which is x, the position, and time. This dV dt is really, you consider a frame where you are co-moving with this fluid element, considering it as a particle. So this Newton law here is for a fluid element, and that means I'm in the co-moving, also called the Lagrangian frame. If you would like to write this in the lab frame, so in the Eulerian frame, what you have to account for is that actually dV comes from the partial derivative of the velocity times dt, and then a term that comes from the gradient, the divergence of v here. Okay. And that brings me then to the Euler frame, which is the lab frame. In that Euler frame, you do have then dV dt equals to the partial derivative and the convection term, which says I have to multiply v with gradient v. That's called the material derivative. And then we really do have the Euler equations, which are now formulated in the lab frame. So the density as a function of space and time times the derivative of the velocity plus the velocity scalar with the gradient v is minus the gradient of the pressure. And all quantities, of course, even if I don't write it, they of course are functions of space and of time. Okay, so that's called the Euler equation. And this is just the formulation of Newton's law in terms of continuum quantities like the velocity field, the density field, and the pressure field. Good, let's rewrite this a bit. So we have two laws here that we wrote down. We have the law of mass conservation, which is here, right? This is mass conservation. And we have Euler's equation expressing Newton's law, and you can combine the two by using Euler's law and inserting it into the Euler equation. And then you see, through a few steps of rather simple algebra, which I won't do for you. I just give you the result. So if you combine this with the continuity equation for the mass density, then you do get an equation which is an equation for rho times Vi, and that is minus del k pik, and del k here is just the shorthand for the derivative with respect to the Cartesian coordinate xk. Okay. Why could I have guessed this? Or why does it have to be like so? Look back here. Exactly. We have momentum conservation the same way as we have mass conservation, we have momentum conservation. Rho times Vi is the momentum. So the momentum, it must be possible to write this in the form of a divergence of a corresponding object, and the corresponding object is now no longer a vector, it's a tensor. And so this is conservation of momentum. I'm not putting it in, I'm getting it out because Newton's equations obey momentum conservation. So what is pik? I know what it is because I've calculated it, but even if I wouldn't, I could write it down. Why? This is a theory that has rotational and translational invariance. So if I write down like vectors and matrices, they're actually tensors, and they have transformation properties that respect these symmetries. So this object that you have here must be composed of invariant tensors, which is delta ik. That's one tensor I can construct. And the other tensor I can construct is just the dyadic, which is Vi, Vk. So that's called, so I don't get it wrong here, that's called the dyadic. And that's our standard Kronecker symbol. But I know the coefficients. That's the upshot of using the Newton's equation. I don't have here arbitrary coefficients that are in front of this. The coefficient in front of the Kronecker must be the pressure. So meaning the hydrostatic effects, they show up in this tensor here as the isotropic, the diagonal part of that tensor. And here, this is the density that appears here. So what we have is hydrostatic part, and the second part is coming from the advection current or the mass transport that you have because the fluid is moving at a certain velocity. Okay, and we call this object here the momentum flux tensor, not the general one, it's for the frictionless fluid. Since all we have is really hydrostatic pressure, so forces and transport. Good, so in order for us to gain some intuition of what these tensors mean, let us again look at some surface element. So how do I draw that? So let's say I'm on a sphere, and on that sphere I have a little surface element, where this here denotes the surface normal vector times the corresponding surface element. Okay. And you have to imagine that this is here part of a larger sphere. Then let's look at the time derivative of the total momentum that's contained in the whole volume here of the system. So I have rho times the Cartesian component I of the velocity vector. And I'm writing this according to this continuity equation that we have here as a integral over volume dk p I k. And now let's again use Gauss's law. Then this becomes an integral over the boundary of my sphere ds k p I k. And now let's visualize that. So what we have here is the surface normal on that. And we do have, let's say this is our normal vector. And let's call this n. And then I can have a certain component of that normal vector. So let's call this nk. And then I'm multiplying this with p index k. And here I denote this with the index I. Okay, so what this means is that the right-hand side, so PIK, this PIK is equal to the ith component, because we have the I here. Okay, the ith component of the momentum flux through the surface so through that boundary delta V. Here we are on this boundary delta V. Of a surface whose normal direction points in the direction of nk. So for example, if you choose to have this to be the 3-axis, where you want to look at the tensor, then Pi3 is the ith component of the momentum flux through the normal, through the surface which has the direction of the axis number 3 in your reference frame. Right? So I hope that helps your intuition of what such a tensor means. We now just continue with all the other laws of conservation that we have. We had mass conservation, we had momentum conservation. Now we look at energy conservation. And this is less obvious. I would say, in terms of how you write this down, because now you really need to use thermodynamics to make sense out of what this here means. So what do we have? No friction still. So we have the temporal change of our density of energy. There's two terms in the energy density. One is the kinetic energy that we have. So it's a half mass density times velocity squared. And then we have the internal energy, epsilon, the energy density per unit mass that comes in here. Okay, so what can I write here? It must again be the gradient of a current. That's due to the conservation law. So it must be the divergence of a current that I now give the superscript epsilon in order to indicate that that's the energy current that we have. Okay, now let's evaluate all these terms. So let's evaluate this term and that term because we know those terms. This one simply from Euler's equation, and that one here because we know the thermodynamics of the problem. And maybe, let me start from there. So let's calculate first dt of a half rho v squared. And let's write this as a half v squared dt rho plus rho vi dt vi. Now let's check what we have. We do have here dt rho. That is the equation for the mass density that we need in order to calculate that. And we have dt vi. Well, that's basically the Euler equation here that you need to talk about when you want to calculate this. So let's insert the mass conservation law and the Euler equation here and there. And then you get minus a half v squared di rho vi. That's the conservation law for mass. And then the Euler equation here is Vi times the negative gradient of the pressure plus rho VL dl and Vi. Okay, now you can write things out and combine different terms. So after one intermediate step, this can also be written as rho vi a half v squared minus velocity scalar with the gradient in pressure. Good, now let's use some thermodynamics. We have the internal energy epsilon that we can consider, but it turns out, and you see why this is the case, we also need to worry about here the enthalpy, which I hope you remember is the energy plus 1 over rho times the pressure. And we know the thermodynamic relations for those quantities. So we know the Gibbs relation for the energy. So this is the epsilon is TdS minus P dVs. And now be careful. So Vs is 1 over rho. It's not the velocity. This here is the specific volume, 1 over the mass density. that we consider here. And we can write this also as T ds. And if I use the relation to rho, this is pressure over rho squared d rho squared. And for dH, we can then also write that dH is TdS. And because this is a transformation, this is now 1 over rho dP. Okay, so this usual back and forth between the different thermodynamic quantities when you want to change the natural variables. Good, now we have things together, and with that we can write the kinetic part of the energy in the following form. So from the analysis that we have on the board, it's the divergence of rho times v a half v squared. And from the second part, so from the velocity and the gradient in pressure, using the relation between the gradient in pressure and the gradient in h, you can write this also as minus rho times the velocity times the gradient of the enthalpy plus rho times t times the velocity times the gradient of the entropy density. Okay, so this here, this quantity S, small s, is the entropy density, not per volume, but per mass, because I'm looking at all the quantities per mass. Good, that's the first term. And what we've used is Euler's equation and thermodynamics. Now let's look at the second term. So dt rho epsilon. I'm now using this relation here for the energy density. And with that, you get rho times t times dt s. That's the first term, so this one here. And plus yeah, so what I'm kind of skipping a step here. Dt rho epsilon, that's a term from dt rho and dt epsilon. And for dt rho, I'm using mass conservation. And for d epsilon, I'm using the thermodynamic relation. And then you do get that this is plus h dt rho. And you can also write this in a more explicit form. Sorry, is that right? Yeah, rho t dt s, and I'm using, again, the mass conservation equation. Then I can write a dt rho here as a di rho vi. Good, that's a bit of algebra that we have to do, but when you combine everything together, we get something, again, that will make a lot of sense when we interpret it. So as we add up the kinetic and the potential energy, sorry, I forgot something here. I forgot the rho here. Then you get that this is equal to minus the gradient of rho v times a half v squared plus h plus rho t dt entropy plus the convective derivative of the entropy. Okay, and now we have arrived at an equation where we can discuss it again. So what we have to have, right, is that this must be the gradient of an energy current. If you look here now at the right-hand side, it's not quite the gradient of an energy current. This is here a gradient of a current. Divergence, I mean, of course, divergence of a current. But then there's a second term that's not the divergence of any kind of current. It is a source term. And if energy conservation is valid, which we assume to be the case, then this term here must be 0 because of energy conservation. There's a way you can rewrite this, right? If you look at that, that's the same kind of derivative as I've used when I go from the Lagrangian to the Eulerian frame. So all you have here is ds dt equals to 0, meaning that for a fluid element in a frictionless fluid to move along, it has to have a constant entropy. So the process in a frictionless fluid has to be isentropic. Well, here, this then must be the current corresponding to the energy density, right? But it's a bit weird, I guess. If you look at it, it's a kinetic term. So you have a transport term, rho times v, that's the mass transport. And then you're transporting the kinetic energy. But you're not transporting the internal energy. It's the enthalpy that comes in here. Okay? And before we go into the break, let me show you what this means. So to see what this means, we again look at a certain volume element and then calculate the expression that we have. So we have this volume V, and we are integrating this divergence, which is the divergence of the momentum times a half v squared plus h. And now remember, okay, before that, let me use Gauss's law and write it as a boundary integral over the surface, rho v, scalar product, a half v squared plus the enthalpy. Now let's look back what the enthalpy is. The enthalpy is the internal energy, but it has this extra term, which is 1 over the density, the mass density times the pressure. So let's use that here and write it accordingly. So this is then minus the integral over my surface times the momentum. And then I do have here indeed what is the transport of the total energy through mass flux, as you would kind of, I guess, naively expect that that's a part contributing to the temporal change of the energy through fluxes that are at the boundary of this volume element. The other part that you have here is minus the integral over the boundary, and then I do have the term which is the velocity times the other part of h, which is 1 over rho p. The rho cancels, so all that remains is the pressure. Okay. What is that now? That's force per area integrated over area times velocity. So that's the mechanical part of the energy transport. So because I'm changing the volume element, I have a mechanical contribution. And this is, so to say, the kinetic contribution coming from the transport through the mass flow in the fluid. Okay, so that's the part where we talked about the frictionless fluid. And let me recap. We have used mass conservation, we have used momentum conservation, and we have used energy conservation. And from all these different conservation laws and using thermodynamics, which was crucial, we could derive a consistent field theory for a frictionless system that's described by Euler's equation, the equation for no entropy flux, meaning entropy is conserved as you advect it along a fluid element. Yeah, that's it. Questions?
And how far does this assumption hold that one always has local thermodynamic equilibrium?
Amazingly well. So that's of course heuristics. You never know how small a volume element should be or how large that those things do apply. But let's say if you think about small systems like in a cell at a scale of say 20, 30 nanometers, it's still valid. And that's pretty amazing, right? So still water molecules are much smaller than nanometers, but still at the scale of proteins, you can, in most instances, really ignore the molecular nature of water and get away with description in terms of fluid dynamics. If you go to a smaller scale, when you really want to know how an individual protein dynamics looks like at the nanoscale of the protein itself, then you need to account for the water molecules in a more detailed molecular level. Yeah?
I have a question about the epsilon. So this is like a potential energy, or how can we think of this? Because we neglected all the interactions, right? There is no further way to store this energy except for the kinetic energy.
There's kinetic energy, and there's, of course, some kind of potential energy that you can think of, such just like in thermodynamics, call it internal energy, and there can be, vibrational degrees of freedom of the water molecules, things like that. That's included. Of course, we don't have at the moment the interaction between the water molecules in a direct way in this analysis. There's some interaction in there, otherwise we couldn't do thermodynamics. But this, what you think of is pairwise friction type of interaction, that's not included yet. That will come.
And also for the specific volume. Could you maybe elaborate again on that? I know it like a change in volume, and now we have a change in 1 over rho. How is it related?
Well, it's just the definition. So I have rho, which is the density, and the inverse of the density I call the specific volume. It's just a name.
Yes, and then why does this thermodynamic relation hold that the epsilon is related to this change in Vs? What's clear is the temperature time.
You just use the usual thermodynamic relations that you find in any textbook.
Which is P, like P times volume change.
Yeah.
And how is volume change related to this?
Well, you just go to a small volume element, and then you're there.
And why is this 1 over rho?
Well, because you're doing you look at a fluid element, and this fluid element then you consider as a system which has a certain density, and at the scale I'm looking at, it's a local scale, these are inversely related.
Okay, yes. So basically each volume element which flows has a constant mass, and then the volume changes scaled to 1 over rho. Okay.
You just apply everything local, and or you put an X at all the thermodynamic relations. That's all you do. You can also see what it means for the system to be incompressible. Maybe you can see it from the equations. So it would mean, right, incompressible would mean that dvs dt is 0. And Vs is related to rho, so you can do this as a tutorial as you like. This means that the divergence of the velocity field is 0. From the continuity equation, you can show that. That's the incompressibility condition. Other questions? Good. After the break, we then study the role of friction, and there you'll see how beautiful Onsager theory comes in.